messaggio in occasione di queste giornate celebrative: non dimentichiamo le cose passate, non dimentichiamo che oggi l'Infn ha in mano 3 grandi progetti, tra cui la più grande macchina acceleratrice del mondo. Noi lavoriamo su temi di grande attualità. La verità che noi cerchiamo si trova al limite di 10 alla meno 33 centimetri, andando dal piccolo al grande. L'altra verità si trova a 10 alla 33 centimetri. Quindi abbiamo in mano 10 alla 66 cose da capire e da interpretare in modo corretto. Se non avessimo queste cose in mano, i nostri figli e nipoti non saprebbero cosa fare, invece no, loro saranno tempestati di cose interessanti da fare, e noi speriamo che in questa tempesta l'Italia abbia un ruolo primario di grande valore.
From the written memories of Eduardo Amaldi in 1925, after my high school diploma, I ended up enrolling in engineering, giving in to the insistence of my parents, who considered the career of a physicist too uncertain and lacking an outlet. I first saw the Institute of Via Panisperna in the autumn of 1925, when I began to attend the physics course as a first-year engineering student. Corbino was an excellent teacher. He taught brilliantly. He had extremely interesting classes. At the end of the 2-year period, he told us, if among you there is someone able to make an adequate effort, this is the right moment to switch from engineering to physics. We have a new professor here in Rome. He is very young and he knows modern physics very well. His name is Enrico Fermi. 1926. Enrico Fermi won the first competition for theoretical physics in Rome. In the years just before, between 1924 and 1926, as professor in charge in Florence, he established a deep friendship and collaboration with Franco Rasetti, assistant professor of experimental physics. The friendship is based, among other things, on the exchange of knowledge. Fermi knows deeply the theoretical physics, Rasetti the art of experimentation. Rasetti shall describe this friendship, a friendship and exchange of expertise. It will be Fermi's adventure. And Laura Fermi, Enrico's wife, wrote in her book about the friendship between the two scientists. The physics laboratories in the University of Florence were in Arcetri, on the famous hill where Galileo had lived during the last years of his life and where he had died. Guided by his friend Rasetti, Fermi spent long hours hunting geckos, small lizards, completely harmless. Fermi and Rasetti then released these lizards in the dining room, just to frighten the girls who served at the tables. The two friends would spend hours lying on their stomachs in the grass, perfectly still, staying perfectly still. In 1926, Rasetti too was called to Rome as an assistant to Orso Maria Corbino. The place left vacant by Enrico Persico, who was instead appointed as chair of theoretical physics in Florence. Thanks to their close collaboration, the two groups soon reached international fame in different but strongly connected fields of research: cosmic rays in Florence, atomic spectroscopy in Rome, the Raman effect, and starting from 1932, nuclear physics in Rome. 1929, a few years after the physics lectures attended by Amaldi in Rome, Corbino pronounced, addressing the Roman physicists, the following words: "The mere possibility of new crucial discoveries is to successfully face the problem of the atomic nucleus. This is the real goal of future physics." Fermi soon gathered around him a new group of young and brilliant researchers: Franco Rasetti, Emilio Segre, Eduardo Amaldi, and later, in 1934, chemist Oscar D'Agostini and Bruno Pontecorvo, who had just graduated. A very talented theoretical physicist, Ettore Majorana, also collaborated with the group. And the group soon gained international fame and became known among foreign colleagues as the Via Panisperna Boys, the first group in history to work as a real team. 1931, together with the following the direction of fundamental physics, Enrico Fermi proposed to call to Italy the best minds in the world or in the field of fundamental physics, around a question that was apparently simple but without an answer, that until then had remained unanswered. What is the actual structure of the atomic nucleus? The first international conference of nuclear physics was held in Rome, partly at the Palazzo della Farnesina, head of the Accademia d'Italia, and partly at the Institute in Via Panisperna. It was attended by several Nobel laureates, aside from Enrico Fermi, who had won the Nobel Prize in 1938. We had Owen Richardson, a Nobel Prize in 1928, Robert Millikan, 1923, Marie Curie, a Nobel Prize winner in 1923 and 1935, Guglielmo Marconi, who won it in 1909, Niels Bohr, who won it in 1922. Of the 7 speakers, the only Italian was Bruno Rossi, who gave a presentation on cosmic rays. The scientific importance of the conference would be huge in the history of physics. 1934, the results of the research of the group of Via Panisperna on the production of new isotopes are at the height of success. Eduardo Amaldi tells of the evening when the group discovered the effects of slowing down neutrons. That very evening, all our friends came to our house because we wanted to write down, take note of the results of our experiences, Fermi was trying to dictate, but he was constantly interrupted by someone who wanted to either add or remove some details. There was a girl at home, a young maid who took care of the baby. That night she asked my wife if we were drunk. Of course we were not drunk. We were simply very excited about the discovery we had made. 1938. The year when Italy passed the racial laws. Between 1935 and 1937, Rasetti, Pontecorvo and Segre had already left Italy, and at the end of 1938, Fermi went to Stockholm to receive the Nobel Prize, conferred to him for the identification of new elements of radioactivity and the discovery of nuclear reactions via slow neutrons. And then he continued to the United States, where he settled and took citizenship in 1944, since his wife Laura had Jewish ancestries. In the summer of 1939, Amaldi, having spent some time in the United States, wrote, after the beginning of hostilities in Europe, the American authorities suspended the departure of all ships to Italy. Ginestra was pregnant with our 3rd child, Francesco, and I was concerned about being able to return as soon as possible. At no other time in my life have I felt as distressed as I did during those 10 days. I came back knowing that our group no longer existed. I had no hope of being able to leave fascist Italy in the following years. I was heading for a Europe at war. The war into which our country would shortly be led, were still on the wrong side.
Subito dopo la partenza di Fermi,
immediately after Fermi had left and all other scientists, especially physicists, left Italy in 1938, there was a Great Depression, which lasted several years. And today, several years on, we can say that those efforts were positive. Today in Italy we have
fiorente
a
scuola di
thriving
fisica
school
moderna.
of modern physics.
Non è solo più a Roma,
It's not
non è
only
solo
to
più a
be found
Firenze,
in Rome
è
or
in
in
molte
Florence, it's to be found in
università italiane.
many Italian
E i giovani
universities.
che lavorano
And
oggi,
young
che sono
people
nati,
who are working today
molti di
and
loro perlomeno dopo
who
la
were
partenza di
born,
Fermi,
many of them after Fermi had
certamente
left,
sono in grado di
are
affrontare
surely
problemi di
capable
fisica
of
veramente difficili
tackling some
e di
very
apportare
difficult
il loro contributo
physics
allo sviluppo della
problems,
fisica moderna.
therefore contributing to the development of modern physics. Good evening. Thank you, Beatrice Skiros, for reading out the first presentation. So welcome to the inaugural event that celebrates the 70 years of the Nuclear Physics National Institute, which has somehow taken on the heritage of the Via Panisperna School, and which has built the extraordinary success of Italian physics and of particle physics. We are here at the auditorium, Fondazione Musica per Roma, in the Sinopoli Hall. So I would like to call on stage the Managing Director, Daniele Pitteri, for a first welcome. Good evening, Madam Minister, Mr. Zoccoli, and everyone in attendance. We are very pleased to have you here with us tonight. We know it is a very important moment for such a solid institute, so important for Italian research. And so we are very glad, because we have been collaborating for many years with the Institute, and this is clear to be seen in the Science Festival. And as you can see tonight, there are some artistic moments as well. I am truly very pleased to have you here with us tonight, because the past year and a half has been very, very difficult, especially for the show business, for art, for music, for live performance. So the scientific community's ability to break off and focus on important problems has been extremely important for us as well, because it has allowed us to carry on, to move on in this year and a half, to experiment something new, to avoid focusing too much on what used to be the normal relationship, our pact with the audience. Therefore, looking for new kind of audience. We have experimented a lot, as other stakeholders have done. The Science Festival has carried on. We didn't have it in present last year. It was organized in remote, and it worked actually very well. It involved the whole entire Italian scientific community, with the Italian Space Agency, the Nuclear Physics National Institute, and other scientific partners. And they truly did help us. You helped us, because you helped us resort to a new method, which is not necessarily tied to the manual aspects, but is linked to the attempt of envisaging something new that might work, that can allow us to move on, to fuel our hope for the future. Science over the past year and a half has been, for some, disastrous. For some, it has been a guide. For me, it has been a guiding light, because it has helped us understand that we are now living in a new world, in a different world, where science is not something abstract. It's something very concrete, very tangible, that helps us address daily issues. So, and for us too, we work in the show business, and if we can have all this, these beautiful lights, this is all the result of scientific efforts that can be seen here today. So if we manage to understand that science is all this, so after a long path, science becomes something we experience on a daily basis, something that can help guide us. This can help us better understand the current debate. which sometimes may otherwise lead us astray. We must always bear in mind how effective, how tangible scientific research is for all of us. So I thank you. I thank you for everything you do. I thank you for being here with us tonight. I thank you for accompanying us, for being our partners in this great adventure that has been going on for 16 years, the Science Festival, and I hope there will be many more years to come to celebrate together. Thank you, Mr. Pitteri, for introducing the topic, stressing the link between art and science. We have someone else to call on stage, and Mr. Antonio Zoccoli, president of the Nuclear Physics National Institute, who will officially open the event. Thank you. Good evening. I thank the Minister, Ms. Christina Mesa. I thank you all for being in attendance. So it's 70 years. That's quite impressive. We have seen the footage, a bit of history in the footage. If we were to say when everything actually began, we should actually go back to 1931, 20 years earlier, when Fermi organized a conference in Rome. His question was, what is the nucleus made of? There are some electrons. We are not sure how the nucleus is made. So we called a whole lot of scientists from all over the world to come up with an answer. Since then, the National Institute of Nuclear Physics was born, and it was one step at a time. Just like the great explorers used to set sail at sea, shifting the boundaries of the known world. We're trying to shift the boundaries of science. And this path has taken us from 1951 to present day, it's 70 years, during which we had a whole lot of successes. We were able to understand better how the universe works. We have Nobel Prizes with Carlo Rubbia, Gravitational Waves, and perhaps next Monday there will be someone else. So it has been a truly very successful path, but what matters is not how old you are, 70, that's quite impressive, but how young you feel. A young person is curious, a young person craves to discover something new, he wants to be astonished. So we still feel very young, even 70 years on. So it's great to see where we stand now and where we can look to, where we can head for the future. Thank you. So I now call on stage Ms. Christina Mesa, Minister of Education and Research. Please take a seat. You can sit wherever you wish. Mr. Thank you for accepting our invitation. So I'll start off with a big question. The Infn is an excellency of Italy. What characterizes this? The excellencies of Italian physics, of particle physics, and generally speaking of Italian science and research. Well, good evening, and thank you for inviting me. So happy 70th birthday. What characterizes Italian science and physics? We've seen this in the footage. It is a fascinating story, very important story for everyone, for all of us. The history of physics starts already. You can see the importance of physics in the degree courses, because it is a syllabus a degree, a course that is open, that encompasses a whole lot of problems. So technique takes the back seat in this regard. The main point is to identify the major topics and to set up the proper methods to address these topics without ever losing focus. This is a typical element of physics. I too, as a doctor, I've dealt with a whole lot of physicists. And I must say this leads, when it actually comes to putting in practice what you have learned at university, allows you to avoid losing focus, which is absolutely paramount in research. And secondly, it's about working, cooperating, teamwork, but variably, because you can also work on your own. There are very different types of physics. Theoretical physics involves more work on your own, whereas other types of physics involve more teamwork. But in the end, what we have is a very solid network that works well. And this is one of the main successes of our excellency. So thank you. I have another question. In your opinion, what are the strategically winning resources in terms of human resources and economic resources if we look at investments in research? Well, basically, we have to fund research, obviously. Today, for example, on the website of the ministry, we have the first Italian national call for tenders that aims to fund fundamental research only. It's about a fund allocated, 50 million fund allocated by this government starting from next year. So possibly the figure will go up. And it follows in the wake of the ERC. So for young researchers, it is very important. And it is one of the methods we have to give our researchers, to stimulate our researchers and help them develop new projects which are associated with the activity of the researcher itself. But there is more. I think we need to plan things better. We cannot simply fund and organize research without being consistent. It cannot be so inconsistent, because when you govern, you might not know what the budget was the previous year. I'll take note of that, because Minister speaks about certainty of resources is quite something. Well, we have to look ahead and plan for at least 5 years. Research would be very different. That would be a big change of pace. A big change of pace. Talk about change of pace. Clearly, in the history of the Infn, not everything has worked seamlessly the whole time. Have there been some changes in pace over the past 70 years? Or not how many? Well, there have been quite a lot, actually. Some discoveries are totally unexpected, and they allow you to understand that there is a field of research you might not be aware of. You might have suspected it existed, but you were not certain. You could not be certain it actually did. So we started studying the nucleus, from which we take our name, Nuclear Physics Institute. We started studying the nucleus, then we looked at the matter, then we studied universe. So expanding our views, always trying to answer new questions. And the more questions we asked ourselves, the more answers we found, the more we realized there was more to be found. For example, one of the very first results, which was somewhat expected, but yet surprising, the quarks, the quark families were not 3, but 4. when we found the quark charm or the J psi particle. I'd like to point out something else. What allows you to make that extra leap in research, aside from the great idea or something you discover while you're looking for something else, is that in order to progress, you need to develop cutting-edge technology. All the great discoveries were made when a new cutting-edge technology was developed, which allowed us to access to new information. We started back in 1600 with telescopes, for example, and we discovered Jupiter's satellites, Kepler's, and as we developed new tools, new fields would open up, as if we're adding new senses to our, aside from eyesight. And this is true for research as well. When we develop new accelerators, we can look to new sources of energy. We can get closer to the origin of the universe and zero in on matter itself and on the structure of the universe. So what matters is not just a change of pace in knowledge, but in technology, because the two things go hand in hand. And quite often a leap in technology allows you to make a leap in research. And we know that technology has a whole lot of spin-offs from technology, from CERN and fundamental research. What are the projects of the Infn, the main project? Now, well, I could talk about this for an hour, but actually we only have 3 minutes. So as I was saying, we have to take one step forward compared to what we know now. We discovered Higgs boson and gravitational waves, and we must expand our field of research, basically. So after Higgs boson, we must understand better the relation between matter and antimatter, what's in matter. So build a new accelerator, new collider, and Fabio Giannotti will talk about this, a greater accelerator to better understand the mysteries of matter and the universe. So we have discovered gravitational waves, and gravitational waves open up new frontiers in research. We used to look at stars through a telescope, then we started using X-rays, gamma rays, infrared, ultraviolet, all bandwidths of electromagnetic waves, all frequencies, and we started using neutrinos, and now we use gravitational waves. And gravitational waves provide you with extra complementary information on the universe. So it's like having a whole lot of messengers coming from deep outer space, which provides with information, and this can allow us to develop the Einstein telescope, for example, which could be a new infrastructure to be placed in an area with low seismic activity, for example, Sardinia. So we have suggested the idea of building this great infrastructure, and I've heard from Christina, and I'm in contact with the minister, and she listens to our proposals very carefully. And so we'd like to develop new accelerators and colliders. We have a project, innovative project in Frascati, Praxia, for innovative techniques to accelerate particles in very little space. We can talk about the Gran Sasso laboratories. I could go on forever. No, I'm sorry, we have to stop, because it's interesting to know that you're in touch with the minister for the Einstein telescope to have it placed in Sardinia, where there is low seismic activity, clearly. Okay, Minister, let's talk about the recovery plan with the European funds. What are the investment strategies with reference to scientific research? I will simply talk about research-related aspects, but bear in mind that research also means training new personnel that works on research. So researchers, technicians, and so on. So we definitely need to purchase and develop new tools, but we need the proper personnel. and this is something we are currently lacking the due expertise in this regard. So about 11 billion euros shall be allocated to research for Mission 4, and 5 billion of them will be allocated to fundamental research. 6 billion to other research, which is closer to the productive, to production and the market. Guidelines will be published tomorrow, concerning this revolutionary kind of research, how to apply for it. Firstly, the 6 billion will be allocated for no more than 60 projects. So we will need a huge cooperation effort in identifying the best partnerships that can achieve all this. I don't think that scattering these funds would be the best things. We must be able to use funds to bring our research, development and innovation levels as high as possible and keep it high in the years to come, because the recovery plan is a unique opportunity, but we must make the most of it in the long run. So few projects, few large important projects with very solid partnerships. The second aspect is that all these projects require cooperation with the research institutes, academic institutes, universities and enterprises. So great public-private partnerships. This is something we have definitely done in the past, but we've always had problems doing it. It's always been very difficult because there are a whole lot of restrictions that hinder this public-private partnership, and we created them ourselves over time. So today we talked about it at the government meeting, so we are planning to bring about changes in how we organize our work. Regarding basic research, aside from the one we already know, there is an interesting fund for young researchers who won the Marie Curie or Silovex, a fund of 600 million, and I would like to use that to give universities and research institutes the possibility of doing proper research. Well, must we give these young researchers a proper job? We must guarantee research independence and give them an idea of what the career opportunities are. So this entails a whole lot of reforms that indeed we are working on to meet the deadline. So I think this plan is definitely to be appreciated, the whole lot of scholarships that take you from the flagship projects of the European Union. So a very ambitious plan, and I wish you the best of luck. I think we all need it. So thank you very much, and I thank Antonio Zoccoli as well.
You have to write this down. I expect that by the end of this evening I will fall down that step. I would like to invite Beatrice Esquiros so she can entertain the audience with a second reading, and we can kick off the second part of our evening. 1935, Japanese physicist Hideki Yukawa came up with the hypothesis that the forces that shape the structure of atomic nuclei, i.e. the interactions between protons and neutrons inside the nucleus, are due to the exchange of an unknown particle 200 times heavier than electrons. As an apparent proof of this hypothesis, the following year, two American researchers, Carl Anderson and Seth Nettermeyer, discovered a particle that was endowed with that kind of mass. They called it mesotron. The math added up as expected, and the physics community became convinced that it had reached a major milestone in understanding the structure of the atomic nucleus. But the discovery of the mesotron actually would pave the way for a new field of research. Oreste Piccioni now. My initiation to the mesotron took place in 1940 in the Italian mountains near Cervino, when I was helping Gilberto Bernardini, Bruno Ferretti, and others with kind of an average level of enthusiasm, except for skiing. It was only when I saw in 1941 an article by Rasetti that my enthusiasm rose to a high level, and fortunately Conversi joined me, Marcello Conversi. Piccioni and I, at the end of 1941, when we decided to work together, well, we had in mind the direct determination of the mesotron's half-life. Piccioni, who was a little bit more experienced than myself, he had a deep knowledge and great enthusiasm for electronics, and most of the development that followed was due to his great expertise. The task of developing an appropriate technique was hard enough as it was, and was made even more cumbersome, of course, by the conditions that were mandated by the war. Summer 1943. After the bombing of the Roman neighborhood of San Lorenzo near the university campus, a group of very young Italian scientists, Marcello Conversi, Ettore Pancini, and Oreste Piccioni, decided to move their experimental gear to the basement of the Virgilio High School, which was considered safer because it was close to the Vatican. The goal of their research was to measure the half-life of the mesotron, the new particle that had been discovered earlier on the other side of the ocean. Once again, in 1943, Amaldi wrote in his memoirs of his experience at the Institute. There was one project that we wanted to pursue at all costs. This was the experiment on the measurement of the mesotron's half-life. Marcello Conversi came up with the idea of the Virgilio High School in Via Giulia, close to St. Peter's. That's how we got in touch with the school's principal. The equipment was assembled on a hand-pulled cart and transported or carried from the Guglielmo Marconi Institute to the high school. In the makeshift laboratory of the Virgilio High School, we started measuring the absorption of mesotrons in matter without Pancini, whom, in the meantime, actively engaged in the anti-fascist struggle, left as commander of the GAP in Veneto. Immediately after the liberation of Rome, the experiment returned to the university, and starting in the spring of 1945, Ettore Pancini once again started working on this project once again. 1946, after a year of uninterrupted measurements, Conversi, Pancini, and Piccioni came to an astonishing conclusion. The mesotron could not be the Yukawa particle, the mediator of nuclear force. What now had become a certainty for the community of physicists around the globe basically collapsed in the face of measurements that were made under the bombs in the first post-war year. The mesotron, in fact, despite having the expected mass, did not interact with atomic nuclei, and Conversi himself later on stated that this result was so unexpected that the three scientists initially believed that there was some malfunction in their equipment. Bristol, 1947. Three physicists were studying the traces left by cosmic rays on their photographic plates. They were Giuseppe Occhialini, who was trained at the Accelerators school with Bruno Rossi, Cecil Powell, an Englishman, and Cesar Lattes from Brazil. The analysis of the many images that had been collected showed that the mesotron is a corpuscle produced by disintegration of a slightly heavier particle, the pion, which interacted with atomic nuclei and rightly took on the title of a true Yukawa particle. There was the proof that the particle studied in Rome by the three young Italian scientists was something new, unknown, and unexpected, similar to the common electron, but 200 times heavier, a new particle that was baptized or christened with the new name, muon. Edoardo Amaldi would later state, the main architect with Gilberto Bernardini of the survival and development of Italian physics in the post-war period, keeping this experiment working at all costs had become a kind of symbol of our wish for cultural and political continuity. 1968, US scientist Luis Alvarez received the Nobel Prize for his research in particle physics. In front of the King of Sweden and scholars from around the world, he thus began his speech. I would like to say that modern particle physics started in the last days of World War II, when a group of young Italian physicists, Conversi, Pancini, Piccioni, who were in Rome hiding from the German occupation forces, began a fundamental experiment. Thank you again. Oh, wait a second. These were new particles that had never been observed before. What were these corpuscles? Were there electrons or protons, or were they new particles that had never been observed before? Thank you again, Beatrice Schiros, for her second performance. And now I would like to call here with me Luciano Maiani, Professor Emeritus of Theoretical Physics at Rome University La Sapienza, President of INFN between 1993 and 1997, and between 1999 and 2003, the second Italian Director General of CERN. Professor Maiani, good evening. Please join me here. Does this work? Okay, let us make ourselves comfortable. In your career as a scientist, you face many, many challenges, and I would like to present you with a worst challenge. First question for you is, how did we get to the INFN of today? But you have 4 minutes to answer. Well, you heard earlier about the first steps of Italian physics in the post-war period, but we have to remember that Fermi, Rasetti, Bruno Rossi, major scientists before World War II, they had established full-fledged schools. And these schools actually were able to grow during the war, albeit in an isolated fashion. Rome, of course, pursued its own journey, but there were other centers, Padua, Milan, Turin. And after World War II, these physicists once again met, and they basically took over Italian physics. And they started with a laboratory on top of a mountain, the Greyhead Laboratory on Mount Cervino, where cosmic rays were being studied, as we heard a few minutes ago, thanks to Beatrice Schiros. And there, new generations of scientists were trained, Carlo Rubbia, Ettore Fiorini, and so on and so forth. The next step was to gather all these teams together in one single facility, which was the National Institute of Nuclear Physics. It's called nuclear because back in the day, still, the nucleus was basically a new frontier, although a new frontier was emerging, particle physics. And the starting point actually was the experiment made by Conversi, Pancini, and Piccioni. And from that moment on, INFN, well, the hallmark of INFN was the fact that it was able to set up major infrastructures, such as the Frascati synchrotron. And Giorgio Salvini, in just a few years, he was able to create a machine which was really at the cutting edge of technology, and then everything else was history. It almost happened spontaneously. At least this is the feeling actually we had. You mentioned Giorgio Salvini, one of the founders, together with Edoardo Amaldi, Gilberto Bernardini, the founders of INFN, and they were amongst the staunchest promoters for the establishment of CERN in Geneva. How did that come about in 1954? Because INFN started before CERN, actually, right? Yes, INFN was established earlier than CERN. CERN was established because basically was the merger between two major issues or problems. How to keep science in Europe alive, since science had become so massive in scope, going beyond actually the size of individual nations. And at the same time, how could Europe be basically be put back together as a cultural and political entity, which of course had emerged in tatters from the war. And so these major scientists, well, they had the good fortune of meeting with great politicians. And from this encounter, well, this CERN was born. And I would like to mention only one interesting thing at this point. Italy had tried to suggest a place where to establish CERN, which was Como. And actually, this proposal was looked into, but this was during the Cold War. That was a time when people identified our physics with the physics of the atom bomb. And in Como, there was really a violent reaction, especially on the part of left-wing parties against this project, and the mayor gave up. The same reaction happened in Geneva, but the situation was solved through a referendum. And the referendum actually approved the establishment of CERN, which was pushed out towards the outskirts of Geneva, close to the border with France. And this was the good fortune of CERN, because this has provided CERN an area where in the 20, 30, 40, 50 years where it became active, this is where these major and large machines were developed. Large machines, sure. Let's take the opportunity to mention that CERN, right, the development and growth of this major European research center, well, this was supported massively by Italy, many Italian scientists, both basically as leaders, as managers. We have two Director Generals of CERN, one here right now and one will join us later on. And they hail from Italy, both of them. But also from the standpoint of research, let's mention Carlo Rubbia, Nobel Prize laureate 1984, because he discovered the mediators of weak interaction. We have a short video clip memorializing this. Well, if we can now show this short video clip, then we'll move on with our very interesting conversation. Can we go on without the video clip? Okay. So 1984, once again, intermediate vector bosons. And this was a major discovery that was reached thanks to the visionary, let's say, outlook and what you physicists call the standard model. This explained, in a way, or favored this major discovery. Well, standard theory or standard model developed starting from the 1960s, and I must say that Enrico Fermi in 1949 already had an inkling of that, thinking that nuclear particles that we see, that they actually were compounded states of other simpler particles. And in the 1960s, these were identified as quarks. But then a theory, of course, needed to be developed. And at that point, I must say that a major role was played by what we call weak interactions. And amongst these, I would like to mention, and this is why I would like to mention Nicola Cabibbo. He included these weak interactions of quarks within a pattern that could give rise to the hypothesis of, let's say, unification of nuclear forces, which happened actually. There were several ideas, the theories by Weinberg, Salam, Higgs, Glashow, and others. And the underlying principle of this is that these interactions were mediated by new particles that were seen as things that we would discover who knows when. But then this idea emerged of these collision rings that was, they came about within INFN thanks to Bruno Tuscia and his co-workers, and Rubbia basically came up with this ingenious machine where he put all this into practice, where protons and anti-protons collided together. And there he obtained enough energy to create intermediate bosons. It was an extraordinary breakthrough that we have all experienced with great enthusiasm. It seemed as if we had reached the frontiers of physics, and actually that was the case. And in just a few years, this theory was developed, which to date basically answers all questions we might ask regarding particle physics. What will happen next? Who knows? Maybe when the next certain machine will be unveiled. Oh yes, that will be for the next episode. But indeed there will be something more that we should expect. Would like to thank Mr. Maiani for this brief but passionate walk back down memory lane. And he reminded me that in 1984, thank you, Professor Maiani, he reminded me that in 1984, I was in my sophomore year in college. What have we lost? Oh, the video clip. I know that we have one. Well, I was a sophomore in college, and Carlo Rubbia held a workshop, a seminar in Carlo Rubbia. It was packed like a Genesis concert. But now, after this brief recollection I had, but Maiani says something interesting. INFN became characterized as an institute that was able to... Okay, now we have the video clip, apparently. No, later? Okay, let's check it out. As if in this collision, instead of having two wrecks at the end of the day, the end result is two new cars. So as I was saying, the collision process is a wonderful process and quite constructive, I would say. As a matter of fact, it's completely different from the idea that you might have, right? If you think about a collision, like a car accident, right? At the end, the two cars leave a wreck in their wake, but two elementary particles, when they collide, they produce several objects. As if in this collision, instead of having two wrecks, in the end result is two new cars plus 35 bicycles and a truck, a horse, and whatever. So in a way, this collision process is a creative process par excellence. And in these very violent collisions, it is there that these wonderful things are being produced, so intermediate vector bosons. Please forgive me, I was thinking about the next video clip, not the one with Carlo Rubbia, featuring Carlo Rubbia. The next video clip, because Luciano Maiani, as I mentioned earlier, he mentioned the great ability on the part of INFN to build the major facilities. And if we go back to 1979, the labs of Gran Sasso were established, and this was the brainchild of Antonino Zichichi. Let's check out the video clip. It was and still is a stellar collapse. There are supposed to be 3 or 4 each century. We're lagging behind 4 centuries because the last one who observed the stellar collapse was Galilei. So there are about 10 stellar collapses that are missing in action, in a way. So we can't wait, really, to make this major discovery and major neutrinos from stellar collapses. The most interesting thing that was achieved in Gran Sasso, I believe, believe, was the study of the oscillation of solar and cosmic neutrinos, and quite soon the ones that are artificially produced in CERN, or in CERN, actually. Well, to talk about the National Laboratories of Gran Sasso, I would like to invite here with me on stage Lucia Votano, and the emeritus head researcher and director of the Gran Sasso Labs until 2012. Shall we switch places? I'm sorry for Luciano Maiani, but I should not be here and then take center stage. Good evening, Lucia. So we spoke about Bruno Rossi, and we were wondering about what the mysterious cosmic radiation was that was being recorded by his instruments. Then we moved a few kilometers underground to try to shield that cosmic radiation because it had become a nuisance to look for signals of rare events. What happened down there? I must say that it went quite well. This was a winning strategic decision that was made, that of building already in the 1980s a major research infrastructure like the Gran Sasso Laboratory, which still is the largest and most important in the world. As you were rightly saying, the decision was made at the end of the 1970s. And then back then, the president of Infn, Antonino Zichichi, took on this project. And it was built in record time because in 1987 the foundations were laid. And between the end of the 1980s and the early 1990s, the first experiments were carried out that were essentially dedicated to the neutrino physics, this mysterious and elusive particles which back then had become actually the protagonist of, let's say, a thriller in science, the disappearance of certain numbers of muon and electronic neutrinos, respectively, the neutrinos coming from the sun or the ones coming from the atmosphere. This was so intriguing for many physicists who, bit by bit, realized that the culprit was, well, neutrinos, actually their ability to transform from one kind to the other. There are three known types, and this was the quantum phenomenon of oscillations. There was a major success of particle physics because oscillations can happen only if neutrinos have a mass, whereas the standard model stated that they did not have a mass. Neutrinos did not really stop there. Gran Sasso gave major contributions, both when it comes to solar neutrinos initially with Galax Genot, and then with Borexino, an extraordinary experiment that measured the entire spectrum of neutrinos, unique in the world. And the oscillations of muon neutrinos, first with macro and then with opera, that used muon neutrino beams coming from CERN. And neutrinos are still amazing. And they are the main, once again, suspects in another thriller, the disappearance of antimatters in the very first moments of life of the universe. We know that at the beginning of everything, matter and antimatter, they were equal amounts. But then some asymmetry occurred in the laws that regulate and govern interactions between particles, which ended up making sure that one prevailed over the other. And theory states that the responsibility belongs to neutrinos. However, this theory states that neutrinos, unlike other particles, do not satisfy Dirac's equation, but they are Majorana particles. And neutrinos' Majorana nature can be proven in underground laboratories, namely in Gran Sasso, that now holds a world record with the two Cuore and Gerda experiments with the double beta decay of tellurium or germanium isotopes. The other major topic that is being studied at Gran Sasso is the dark side of the universe, and more specifically what we call the direct search for dark matter. We're looking for collisions between dark matter and our detectors that are made of regular matter, of course, ordinary matter. And here, once again, Gran Sasso holds a world record. Not only are there different experiments going on with different techniques, but the Xeno experiments is the one that gave the best limits on the interaction between some candidates for dark matter that we call WIMPs. The other very important thing is that both in the double beta decay without neutrinos and also in the search for dark matter, there are new experiments that are going to be unveiled quite soon. We'll begin quite soon. So I would like to wrap up saying that Gran Sasso had a glorious past, and also good present time, excellent prospects for the future. And this is the living proof that building major research infrastructures at the right time then allows schools to thrive, that then allow us to reap a lot of success. Well, thank you, Lucia Votano, for this wonderful and concise presentation she gave us. And she touched upon two subjects that I believe are very fascinating, both neutrinos and dark matter. And they were very fascinating for an extraordinary visitor to the Gran Sasso laboratories a few years ago. We have one more reading. I would like to involve Beatrice Sciros, Umberto Petrin, and by Andrea Camilleri. Let's see here about the laboratories of the Gran Sasso.
Con grandissimo dispiacere di me.
Much to the chagrin of my father, who was a physicist and mathematician, I arrived at the third grade in high school, actually, still unable to memorize multiplication tables. Imagine if I could tackle trigonometry or physics. I must confess that as the years went by, I always regretted that I could never understand anything about math and physics. As I got older, I began to judge this inability of mine as a real inborn impairment, a birth defect, a terrible disability that prevented me from a wider understanding of the world. In fact, the good literary knowledge I'm endowed with can only explain in part human behavior, but it cannot enlighten me at all on elementary daily phenomena such as the sun, air, light, earth, and fire. Basically, I'm a half-blind representative of one of the two cultures that now yearns in vain to know a minimum, something of the other culture, because I think that I would be enormously enriched by it. So, to make up for this shortcoming, I assiduously read the scientific pages of newspapers, and for what little I can understand, I get excited at every new discovery, at every new scientific adventure. I'm like a fan who cheers on the sidelines, but would not be able to kick the ball. Therefore, the fourth time since I was lucky enough to have a second chance, I enthusiastically accepted the invitation to visit the Gran Sasso laboratories. I must confess, when I walked in, my heart was racing, and it started beating even faster as soon as I realized how huge those underground laboratories were. The first impression I had was that of seeing three huge living cathedrals placed one next to the other. Well, I'm not a believer. I was overwhelmed by a sense of secular religiosity. While scientists were talking about ongoing research, among which one that would have sent neutrinos to Geneva, I was enthralled by the wonderful names with which the different research projects were designated, names that were certainly pertinent to different specificities, but that opened my imagination, transformed the great equipment in immense suggestions, able to transport me much more than common spaceships in a fantastic journey towards the sun and the stars. A lab of this magnitude immediately plunges you into filmic unreality. You feel like you're on a set from a 007 movie, but it's real, it's not fiction. You can see it. Then the director explained to me something that moved me to tears. He said that they were having a hard time in analyzing particles because of their mutability, because they easily infected each other, and therefore they had to be filtered through pure lead. Lead that could no longer be found. However, the director told me that off the coast of Mazara del Vallo there was a sunken Roman ship and was filled with Roman lead. And that was pure lead. They recovered a certain amount, and this allowed the highly advanced laboratory to continue with its research. A piece of Roman metal dating back from 2000 BC. This lightning-fast welding between past and present that leads you on a quest for the future was dizzying. Actually, I must confess that I was deeply moved that this was happening in front of my very eyes. There I had the feeling of the eternity of time, space, the universe, infinity. It was like a flash of lightning. I'm not a poet. If I had been a poet, maybe I would have written a poem about this, because as Rilke used to say, the first verse comes to you from God. All the others, the ones that follow, are your own business. There. Well, but there, the first verse was somehow suggested to me.
Grazie ancora Beatrice Schiros.
Thank you, Beatrice Schiros, and I would like to thank Umberto Petrin, whom we saw for the first time, and now we should invite another President Emeritus of INFN between 1998-2004, President, Professor at the La Sapienza University from Rome, and Enzo Iarocci should be joining us in his house. Well, Professor, we heard both the testimony of Antonino Zichichi and Professor Votano. Neutrino physics plays a central role at the Gran Sasso. During your presidency at the beginning of the new millennium, you promoted a fundamental experiment that would then bring CERN within Gran Sasso, CNGS, an ambitious connection between the equipment in the Gran Sasso that were supposed to receive neutrinos that were sent from CERN in Geneva. Why this experiment happened? Why were you such a staunch supporter of this experiment? Well, neutrinos directly from CERN to Gran Sasso. Back in the day, the Director General of CERN was Luciano Meiani, so there was some, let's say, teamwork between Gran Sasso and CERN, since we belonged to the same team. We were on the same team. The problem was not basically to produce this beam. This was in our reach, technologically speaking. I'm talking about both CERN and Gran Sasso. However, the experiment in Gran Sasso that was supposed to reach the goal of the project, that was the point. Starting from a beam of muon-type neutrinos, let's say the siblings of the muon that were mentioned earlier, because of oscillations mentioned earlier by Professor Votano, in moving towards Gran Sasso, neutrinos were supposed to change type and become tau neutrinos, and the point was that we needed to prove that part of the neutrinos that reached Gran Sasso actually changed type, were of a different kind. So the experiment in Gran Sasso was supposed to prove with absolute certainty the transformation of the starting neutrino, and the experiment was called Opera, and we were supposed to receive this neutrinos. Neutrinos were received at at the Gran Sasso after a journey of more than 700 kilometers through the Earth's crust, completely underground. And about 2 milliseconds were needed for the neutrinos to reach Gran Sasso. What was the hallmark or the specialty for the opera experiment? To be able to identify beyond any reasonable doubt the change in neutrino type, so identify the tau neutrino at Gran Sasso. And it was the use in the experiment of a myriad of like small lead bricks, basically, interspersed with nuclear emulsions. Nuclear emulsions, they are particle detectors like a film, like a photographic film, with micrometer-like accuracy, so that they could identify the tau neutrino. The problem was a massive number of these particles, and the management of the reading of this information. These emulsions were a famous detector in the 1900s, very successful in the mid-1900s. Then it became obsolete because electron-type detectors were developed. But then, once again, this old system was recovered to automate the microscopes that have to exploit the micrometer accuracy of emulsions. In order to start the opera experiment, we needed to set up a number of laboratories that not only were supposed to prepare these detectors, but they also needed to be equipped for this automatic microscopy for the reconstruction of the images of the tau neutrino interactions. A very complicated endeavor, huge investments, both financially and also in terms of human resources. But the good thing was that not only the experiment was successful and was completed successfully less than 10 years ago, after having successfully identified the arrival at Gran Sasso of tau-type neutrinos. But this technology was kind of old. Think about these nuclear emulsions. And this was kind of revived and recovered in order to carry out that experiment. These experiments related to tau neutrinos. And this gave rise to further developments in two different directions. First of all, to develop a new detector of dark matter particles, a detector that would be able to be, let's say, directed in a way. It could point to the direction of the collision between the dark matter and matter collisions. And then a neutrino detector was developed in the neutrinos produced in HLC collisions. And these opera experiment emulsions recently were used also in another activity that's related to the treatment of cancer using hadron beams. The small bricks, like the ones used in opera, building blocks, not made out of lead interspersed with emulsions, but different, let's say, different materials interspersed with the same emulsions, but enlightened or illuminated by carbon ions or other nuclei, proton beams, basically, to depict the fragmentation effects that are related with the interaction with beams. So this is very interesting to treat cancer with hadron beams. So we're happy to see, on the one hand, the results we have achieved, the results that we were pursuing with this project, the neutrinos from CERN to Gran Sasso. And then we're happy because we used kind of an old-fashioned technique, and this gave rise to new developments that perhaps can give very interesting results in the future, either for Gran Sasso or CERN. Interesting because these two research projects can involve both laboratories that have contributed to this development. Thank you. Thank you, Professor Yarocci. Thank you also for having shown to us very briefly how we can go from fundamental research to spin-off and applications that are extraordinary, also and important for human health.
Professor Yarocci.
Now, have a link with Mr. Arthur MacDonald. Professor MacDonald. Very similar to the Gran Sasso laboratory. By the way, you work and compete with Gran Sasso in terms of neutrinos and even in the search of dark matter. Do you do that as well at Sudbury?
La traduzione, ma soprattutto bisognerebbe interpretare il labiale. Professore, non la...
Professor, I'm sorry we cannot hear you. The audio is not coming through. We might have a problem. Something has gone wrong. We might carry on now, and perhaps we could hear Professor MacDonald later on. We have no audio signal whatsoever. Professor MacDonald, I'm sorry. We'll stop here for now. We'll have to interrupt the video link, and we'll go back to Lucia Botano, who will tell us about astrophysics and particles, what links what is very small to what is very big. So these particles are not studied only via underground experiments, right? Indeed, the main feature of particle astrophysics is to how to put together microspace and macrospace. The cosmic model of the Big Bang with the elementary particles models? Well, the answer is rather simple. You have to study the universe by using all the messengers the universe sends. As our chairman was saying, not only the light of the stars, but electromagnetic radiation in all its frequencies, including high-energy gamma rays and cosmic rays, charged cosmic rays, neutrinos, and gravitational waves. So the discovery of the century, I might add. So this study, which is studying the universe through its many messengers, which is multi-messenger astronomy, we call it, is one of the most interesting elements of astroparticle physics, which keeps on opening new opportunities in terms of observation of the universe. For example, we know that the universe is not a calm place. It's actually a place where there are huge cosmic events, massive cosmic events with huge masses that accelerate or collide at almost the speed of light. And these release a huge amount of radiation and energy. And in many cases, I'm talking about collapses, neutron stars, black holes, and these act as cosmic accelerators that accelerate charged particles. But even gamma rays and neutrinos are byproducts of these cosmic accelerators, but they are very important. Actually, they might be even more important because they guide us to the source. For example, in 2017, what happened? We measured simultaneously a neutrino in the South Pole and gamma rays from the satellites. Plus, we have gravitational waves as well. So this very diverse particles that come from outer space require instruments and technologies that must be targeted to measure and gauge a specific type of energy or phenomenon. So astroparticle physics features great measures large swarms of cosmic rays hitting the Earth, but it also builds tools that must be very light and efficient and sensitive to be fitted on satellites or on the space station. And we have underground laboratories, undersea laboratories such as the Infn project CubeNet, which aims to measure energy in the Mediterranean, but even indirect research, so-called indirect research of the dark side of the universe, is done with tools that can be fitted on the space station, for example. But studying the evolution of this cosmic network that holds together galaxies and galaxy masses and dark energy everything is done through tools that are in outer space. Concluding, astroparticle physics has somehow developed, because it has very specific requirements, which is to gauge and measure some very rare events very accurately. It has developed its own innovative technologies, whereas at the beginning it used the detectors of astroparticle physics. So once again, physics, technology and innovation, we can see, go hand in hand. Thank you, Lucia, for telling us how we study the universe. Only 4 centuries ago we called it the sky of the still stars. So Professor MacDonald is available now.
Yes, can you hear me?
Buonasera.
Good evening.
Hello, can you hear me?
La sentiamo perfettamente.
Yes, we do hear you. We hear you perfectly. So I once again ask you the question I was asking before. The laboratory you founded, Subterranean Neutrino Observatory, it is a laboratory which is very similar to the one at Gran Sasso. You cooperate, you compete both in the field of neutrinos, but even in the field of dark matter. That was our question. Are you looking for the same thing?
I think cooperate is a better word than compete. We all have the same objectives, and so our laboratory was founded originally for the Sudbury Neutrino Observatory, which we were able to use to observe clearly neutrinos from the sun, electron neutrinos changing into other flavors. It then has later been expanded, and we are now doing further work on neutrinos, but also on dark matter. And in terms of the neutrinos from the sun, there was very collaborative work with Borxino, with Galax and GNO in terms of understanding overall the set of neutrino emitting reactions that power the sun, and in the process learning more details about the process of neutrino oscillation. In the case of dark matter, it's very cooperative in terms of the things I'm presently working on, in fact, which are focused on an experiment we are starting construction of in Gran Sasso Laboratory called the Dark Side 20K experiment, which uses liquid argon as a technique to observe the weakly interacting massive particles, or WIMPs, as Professor Votano just described them, in this case interacting with the liquid argon. And work had been done at Gran Sasso on dark side 50, and on a slightly larger experiment in the Snow Lab called DEEP, both using liquid argon. And now at the level of about 100 tons of liquid argon, we are developing the dark side experiment, which will push further the sensitivity and again be complementary to what the xenon experiment is doing in looking for WIMPs as examples of dark matter. So that's a prime example of how we cooperate internationally, but all of those are. But another example that I can mention is the fact that at the time of the start of the COVID pandemic in March of 2020, Professor Cristiano Galbiati, who is at the Gran Sasso Institute in Princeton, and who was locked down in Milan, realized that the technology we had been using to develop our liquid argon detectors could be applied for a new type of ventilator, which would be simpler and less expensive in its nature, targeted at the most severe patients in COVID-19. And 250 of us around the world, including industries and medical doctors in particularly in Italy, but also in Canada, US and other countries, total of about 10 countries altogether. We came together and we were able to develop 7,300 of these ventilators under a contract with the Canadian government. They have now been delivered and are now being considered for donation to countries in need around the world. And so it's an example of how fundamental science and fundamental scientists and engineers who work on these sort of experiments are a resource that can be applied in society when there is a societal need. And we're very pleased to have been able to do that. And we're now all basically back to the process of doing fundamental research with the DarkSide 20K experiment.
Grazie infinite.
Thank you very much, Professor MacDonald, and thank you for going back to stressing once again the importance of technology and research and their links. So I thank Professor MacDonald and Lucia Votano. And I call on stage Umberto Petrin for a musical performance.
L'era atomica è sorta come
The atomic
L'era
era
atomica è sorta come
began
risultato
as
degli
a
studi di
result
vari
of
scienziati
studies of several
in Italia,
scientists
in
in
Francia, in
Italy, in
Inghilterra, negli
France,
Stati
in
Uniti, in
England,
Danimarca,
in the
in
United
Germania
States,
e in
in
altri
Denmark, in
paesi.
Germany, and
E
in
lo
other
spirito
countries.
di
The spirit
cooperazione
of
continua nel
cooperation
mondo di oggi,
continues today
come lo dimostra il
as
Consiglio
the
europeo delle
European
ricerche
Council for
nucleari di Ginevra,
Nuclear
che
Research
accentra
in
le
Geneva
ricerche e le conoscenze
shows.
scientifiche
It brings
dei diversi
together
paesi
the
europei che
research
vi
and
aderiscono.
scientific knowledge and
E si
expertise of
lavorano
the several
insieme
European
seguendo un
countries that
piano
are part
coordinato
of
di
it.
ricerche e avvalendosi di
These scientists work
un'attrezzatura che
together
nessuna nazione da sola
using
sarebbe in grado di
equipment that
fornire.
no
I
single nation
risultati di
could be
queste
able to
ricerche
provide
saranno
alone. The
messi a
results of these
disposizione di tutti. Per esempio,
this
gli
research will be
isotopi
made available
radioattivi
to everyone.
vengono
For
usati
example,
oggi in tutto
radioactive
il mondo,
isotopes are
negli
used all
ospedali,
over the world,
nell'industria, in
in
agricoltura.
hospitals,
Per
in
usare
industry,
le
in
parole del
agriculture.
presidente Eisenhower,
Quoting
troveremo il modo di
President
far sì che il
Eisenhower, we
miracoloso
will find a
spirito
way
inventivo degli uomini non sia indirizzato alla
for the
loro morte,
miraculous
ma venga
inventive spirit
dedicato
of
alla
men
loro
to
vita.
be used not for their death, but for their life. So we thank Umberto Petrin for his musical performance, and I now call on stage Fabiola Gianotti, Director General of the CERN, second term for her, and once again INFN President Antonio Zoccoli. So I'll sit over here. Please have a seat. Good evening. Professor Gianotti. So in 2012, you were at the head of the ATLAS experiment, which announced the discovery of Higgs boson. How did we get there? How did we get to that point? Above all, it was not just ATLAS. It was two experiments that announced it simultaneously, ATLAS and CMS. It took us 30 years. From the very first ideas on the Large Hadron Collider in 1984 to the actual discovery in 2012, so roughly 30 years. The discovery of the Higgs boson symbolizes how our field works, and it symbolizes the virtuous link between research, the wish to answer new questions, and the link with technology, industry, and international cooperation. So we start off from an idea, usually answering a question, a very important question. For example, in this case, understanding the rupture of electrosymmetry. An answer could be Higgs boson or something else. Usually these questions are rather complex. And then we wonder, what tools, what equipment can I use to get to an answer? At the time, we had no specific data, so we had the Higgs boson was not specifically tied to some masses, which allowed us to think it could be light. So we need a very powerful accelerator, a lot of energy, very intense beams, very complex technology, especially with reference to the accelerator with the superconductors. So these very powerful accelerators created very complex situations for the detectors too, which had to be high performance detectors and had to manage a very complex and harsh colliding environment. So that's when the idea of developing new technologies, new tools, new equipment that was up to the task initially seemed quite frankly impossible. But if a physicist or an engineer says it's impossible, then that truly is the assertion that drives the scientists to find a solution to the problem. And those years were very enthusiastic. The 90s, I'm talking about the 90s. There was great enthusiasm. We worked hard to find the technology, to develop the technology and tools we needed to discover this Higgs boson. When you work on the very edge of technology, the path is always uphill. You take two steps forward, one step back, one sideways, so you really have to hold on. You really have to be very tenacious. And the industry played a crucial role as well. The way CERN and the Gran Sasso laboratories work together with our industry is not a relationship that is similar to a customer and a seller. We actually work together. We develop prototypes together in laboratories, together with our industrial partners, the best industrial partners. And when the technology is developed enough, production is shifted on a mass scale. So the industry joined us in a very early stage in the development of the LHC. And another feature of our field of work, as the pandemic showed, is fundamental research. We must work together. So cooperation is paramount. The discovery itself actually came very quickly. We weren't expecting to find the Higgs boson so quickly. We thought we would find something else regarding the symmetries, which then didn't show up, not so far anyway. But 2 years after the LHC was fully developed, we found the Higgs boson. Already in 2011, 2 years after igniting it, after turning it on, we detected a signal with a specific mass, and then in 2012 we got the signal on the whole, and we disclosed it. Where Fabiola Gianotti is a director general, there are about 15,000 scientists coordinated with some Italians too. And there are a lot of Italian scientists. Why is that? Because as Luciano Magliani said, there are schools that were set up in different departments of the INFN, and these schools started gathering young researchers and brought them to the CERN. They started conducting research and experiments. So this formed a group of people working at CERN, and they started working on the very first accelerators, and then eventually reaching the LHC, the great accelerator that allowed us to make the discovery. So we have this community that has gradually grown stronger, has acquired the due expertise from a technological and scientific standpoint, and they came at the moment of the discovery, it was a very strong, very solid community. We had some Italian scientists holding leading positions in all experiments at the time. Fabiola was at the helm of Atlas, and there were other scientists holding many key positions, key roles in these experiments. And a lot of young researchers, highly motivated, working day and night to achieve this goal. And it was a great thing to experience those moments at the CERN in Geneva, going to the refectory together and trying to understand what I was working with Fabiola in the Atlas experiments, trying to understand what stage the other experiment had reached. And you could really feel the enthusiasm that was there, because we could feel the goal was near. We were about to make a huge discovery. I really think this is a unique experience for a researcher. When you get close to discovering something, when you actually make that discovery, that is a huge moment. And all this was possible thanks to the great work that was done starting from the 1950s. The Italian physics school allowed a whole lot of young students to become important scientists and coordinate activities. And this generation will be replaced by future generations. And this is the real asset of the INFN, the ability to teach, train, and renew. Always with a group of students always driven by enthusiasm. Generation after generation. This is a true asset. It is not something that is built in a day. It's something you build over decades. And this was possible thanks to the great leaders of this institute. If I might add, the INFN, from a professional standpoint, is our mother. So we wish it the very best. Okay. By the way, enthusiasm is clearly something that you can really feel when you're waiting, when you're about to discover for something that has been long for decades. And we have a video by that will remind us of this. Gravitational waves, huge. If we had been close enough, it would have moved the tables. Solar masses emitted gravitational waves. Then again, I must say that we don't know exactly what black holes are made of. We know they exist, that's their discovery. There are not only gravitational waves, but we know about the existence of black holes. We think that black holes emit gravitational waves. As far as we know, as far as we're concerned now, that's the case now. And 3 years later, in 2015, the Ligo Virgo cooperation discovers gravitational waves. And there are 3 people that 2 years later would receive the Nobel Prize for Physics, Barry Barish and Larry Fine. And Barry Barish is one of the founders of the EGO experiment in the United States. He knows Italy very well. He has worked with the Gran Sasso laboratories and is part of the Gran Sasso Science Institute. And we have a video link with him right now. Professor Barish, good morning.
Hi. I hope you can hear me.
Barish.
I hope you can hear me.
The discovery of gravitational waves for the first 20 years of this century, I believe it's the discovery of the century together with the Higgs boson. What is the value of this discovery, and what is the value of the wonderful cooperation between the United States and Europe in this respect?
It's very much in parallel to what we just heard for CERN and the Large Hadron Collider and the discovery of the Higgs boson. Both of these, I think, are testimonies to how alive modern fundamental experimental physics is and our ability to learn about the most fundamental laws of nature. At CERN, we learned about how mass is created. We first heard this from Einstein in 1905, that energy equals mc squared. Now we know how we can create mass, actually, by the theory of Higgs and the demonstration at CERN. Similarly, in 1915, Einstein gave us a new theory that expanded our understanding of gravity. And one of the basic concepts of that was that gravity, like electromagnetism, has waves. In electromagnetism, we're all familiar with everything from radio waves to light waves to microwaves. But gravitational waves had never been observed. It was hypothesized by Einstein. The experimental effort to see if they existed began about 50 years ago. So like the Higgs discovery, it took tens of years to develop the experimental ability to actually observe gravitational waves. We succeeded in 2015 to discover gravitational waves. And that was done by an instrument that many claim is the most precise instrument ever built. We measure effects that are 1/1000th the size of a proton. And that is a good demonstration, as is CERN, of the ability of man and physicists to use innovation and modern technologies to develop science and then to use them later in all kinds of ways in modern society. For us, the collaboration between Europe and the US has been fundamental for years, ever since World War II, really, and the development of the CERN laboratory. Certainly the CERN experiments are a strong collaboration, but that collaboration is broader than that. It's really worldwide. So I really think the answer to your question is a worldwide collaboration. Science itself doesn't have any national boundaries. We speak the same language. We have the same problems. We understand the same things about nature wherever we are in the world as physicists. And so bringing them together, to work together, gives us the ability to address the most difficult and the most fundamental problems. CERN is a wonderful example of that. It has worldwide participation. It's a European laboratory, obviously. It's developed and funded through European nations, but its scientific participation is worldwide. Similarly, but maybe a little different, LIGO is a collaboration of experimental research groups from around the world, representing countries in Asia and Europe, the US, in Russia, and so forth. And that, to me and to all of us, tells us that science just has no national boundaries. We all really work together. In LIGO, we discovered, as was mentioned, gravitational waves in 2015. But in 2017, we made another discovery, which was a collaboration of collaborations. We use the word Virgo Ligo. Virgo is a different collaboration. It's a collaboration multinational, like LIGO, but it's totally separate governance, separate leadership. First by Adalberto Giazzotto, who we miss, and LIGO separately, and in some sense we competed to discover gravitational waves. But together, 2 years after we made the discovery of gravitational waves together, we made another wonderful discovery, and that was the discovery of the collision of two neutron stars, which was the first time that we could observe gravitational waves and electromagnetic waves, gamma rays, at the same time and learn how neutron stars work, how they collide, and all this kind of thing. And that was done by using the Virgo observation and the LIGO observation to be able to point well enough in the sky so that the astronomical instruments could see if they saw something at the same place. And they did, and wonderful science came out as a result. So I've worked at the Gran Sasso lab. I've worked with particle physics for years. These are all the kinds of things that INFN has done. And so in a sense, I'm a great beneficiary and friend of INFN, and I congratulate INFN on its 70th birthday. Thank you.
Thank you so much, Professor Barish, for the story you shared with us. And you reminded us specifically that Italy played a fundamental role in this discovery because right from the visionary ideas of Amaldi and then Giazzotto, right? This is another beautiful story, as we already said. 100 years before the discovery of gravitational waves, all this started because Einstein said, if my theory is true, then these waves that spread through space and time must exist, producing these ripples that basically reach us. We were supposed to be able to see this, but these ripples are very tiny. So when INFN was established, then it started carrying out research in this domain as well to develop technologies and detectors to detect gravitational waves. The most simple things is that spatial dimensions change. We must use an instrument that detect these vibrations that are similar. I've simplified the whole thing now. Similar to an earthquake. Then I will set up a giant seismographers, and these first generation gravitational waves antennas that were also built thanks to Edoardo Amaldi in INFN. We use cryogenic antennas with pioneering technologies that we had available to detect gravitational waves. One was in Frascati and the other one in Legnano. But the technology was not advanced enough. So to detect these waves, we changed technology, and we use this new technology, these interferometers. They are gigantic instruments. They are miles long, where we have a laser beam moving back and forth, and we compare the time that the laser takes to go from one direction to another. and they interact with each other, and we realize if the distance has changed in one of the two legs, and we see if gravitational waves have reached their destination or not. This has been the winning technology. And once again, history, or our story, or our history, has been that of an institution that is able to develop spearheading technologies, that initially embarks upon a road which turns out not to be the right one, but then with the technological know-how it has, it follows a different road, builds a major infrastructure. And this is another fundamental thing. Science nowadays can make progress when you are able to build a facility where scientists can work together. And Barry Barish said as much earlier, the fundamental thing is having a place where people can work together. And this has been the Virgo Interferometer. Everybody was saying relativity is true, gravitational waves then must exist. And then after 100 years, it took 100 years of the technology development that we were able to discover them. We discovered them. And what now, right? Yes, 100 years ago, Einstein said that they existed. What should we do with this? And what Barry Barish said is absolutely fundamental. 2 years after discovering gravitational waves for the very first time, we were able to associate information coming from gravitational waves with information that astrophysics detectors and the observatories were able to see in space. And we combined the two things, and for the first time, we saw two neutron stars emerging, and the heavy elements were made, because in solar fusion, then elements up to iron were produced, the ones that we thought that would be produced in events such as this. And this was seen, and this opened a new window in the study of the universe. And all this is done because there is a background before this, because we were able to train young people who have the skills, engineers who have this know-how, and we can develop all these technologies, because most of the technologies that were used, both in Italy and in the United States, were developed here. So Italy played a leading role globally in this domain, and this is really a benchmark. We're used to say that in Italy nothing works. Sometimes there are things that work very well, and we must emphasize this. This is the Italian school, not just for INFN, but the Italian School of Physics is a global excellence and a reference point. Yes, at long last, you said this. Now I would like to stand up, but I'm not just leaving you behind, but we have another guest here. And I would like to welcome now a former president of INFN, I believe the only one for 8 years, right? A little bit less than 8 years. Okay. He between 2011 and 2019, Professor Fernando Ferroni, former president of INFN, welcome. And he was president of INFN back then when those two extraordinary discoveries were made. I'm so lucky. Yes, you've been very fortunate, but what does this entail? Being involved in a research project that does not really have a clear timeline or a clear idea of what discovery, what might out of this. Well, the president of INFN is the representative of a community, and he or she has a task, that of converting the dreams of the community into a reality. The president of INFN, well, he or she could have a brilliant idea. There have been presidents in the past who had brilliant ideas. However, it is the community. INFN works as a very broad community that likes to think that it can address and solve fundamental problems. And I must say that I always had a feeling, ever since I started in this profession, that nobody ever worried about time, right? There is a goal to be pursued. I want to reach that goal. I want to verify law. I want to prove that something works in a specific way or in a different way. This is a journey replete with joy and sorrow. If we could buy technology off the shelf at the grocery store, we would not have discovered anything. We would have not have had INFN. We would not have had the enthusiasm of researchers. It is a work in progress where you have to build your own tools and instruments. When you build your own instrument, you do not think, well, it has to work tomorrow. You know that tomorrow it's not going to work. But you know that this instrument will take you far away, will take you far, it will lead you to fulfilling that vision you had. The fundamental strength of INFN, it is its ability to make a mechanism of experiment selection work, which is an inner mechanism in which we have national committees representing the different, let's say, scientific disciplines. And you have to basically pitch, right, your experiment. And in front of you, you have your peers, basically, your colleagues, and maybe they have projects that are in competition with yours, they are competing with your project. But the power of INFN is that those people, those individuals who should grant you the necessary funding, basically, because the president signs on a piece of paper, does not really get into these details, whether the electromagnetic calorimeter made in a given way or in another way should be funded or not. Your colleagues are also your competitors, quite often. With all the passion they have, they help you to then redesign your detector in the best possible way through this process of critical revision, encouragement, and fierce but constructive criticism. I believe that this is a wonderful way of doing things. It's so different from a situation where you say, okay, you have to do this, get it done. No, this cannot work. This kind of approach, this bottom-up approach that, at least in IFN-FN, this is what allowed us to make progress during the time of big science or the major experiments. This would not work otherwise. The president of INFN cannot say, for instance, build an experiment for gravitational waves. That's nonsense. It is a community that together wants to discover gravitational waves. The president of INFN has a task of helping these people, equip them with the instruments they need, money, let's say, frankly speaking, in order to make their wish come true. And the other aspect behind this is that as you carry out these experiments, as you build your experiment, as you build your know-how and your expertise, and then you realize that you're doing something that has possible connections, that technology that you cannot buy off the shelves, the technology you're building, that technology could also be used for something else. And this is another, really, one of the, I believe, the strong points of your commitment. Not only you have satisfied your intellectual curiosity, which is your prime mover or driver, you cannot really tell someone, okay, build a magnet that's more beautiful than the old one. No. You maybe want to develop this magnet because you want the particle to spin in a different direction. But you do not shy away from this commitment. You will be involved in this transfer of knowledge towards a different use of that technology that will be recognized in some way by society. So it is a complex mechanism, but it is a mechanism which I believe it is perhaps the greatest strength the INFN has. If we could buy the components for our experiments at the grocery store, we would not have this community and these experiments. So thank you, Fernando Ferroni, for your words that are touching, I would say. But he reminded us that the two major discoveries we mentioned earlier, Higgs boson and gravitational waves, they're both discoveries that required a very long gestation, a great determination, and an incredible vision. Is there a new vision, I believe, or ambitious vision on the horizon? Oh, yes, of course. Thank God. Absolutely. The journey of knowledge is quite long. There are new challenges out there, indeed. In fundamental physics, one thing that we are certain of is that there's many open issues. We do not know the answer for this. Many of these questions, we understood the questions even if we do not have the answer yet. We know what we call the known unknowns, the dark matter, mass in Higgs boson, neutrino masses, and then perhaps there are a lot of known unknowns that we do not know yet. And making progress along the path of knowledge is also realizing what are the right questions we might ask, we have to ask. Now we are in a situation in which there is a very clear picture when it comes to our understanding of fundamental physics, which is the standard model that we've talked about. And there are several open questions that were highlighted through new discoveries and increasingly accurate measurements. So think about dark matter. And the important thing that we need to underline is that these open issues perhaps have solutions that are linked together. Understanding, for instance, what dark matter looks like, or the mass issue with the Higgs boson might give us indications about dark matter and vice versa. But these are very complex issues. To date, there is no instrument or tool that we can identify, and so we can say, let's build this instrument, and this instrument will allow us to answer all these questions. It would be wonderful, but it does not exist to date. The best thing we can do is, in some way, try to set in motion all the most promising experimental approaches that astroparticle and particle physics that we carry out at NFN, and it has developed over the years and decades, thanks also to the development of technologies, accelerators and detectors. So we have accelerators, underground experiments that look at particles coming from the cosmos, instruments on the International Space Station, and so on. So accelerators, they have been the main instrument to build from the standard model from the experimental standpoint when they replaced the study of cosmic rays in the mid 1900s. And they will keep playing an extremely important role in the future as well. We really cannot think that we will be able to answer these open questions without accelerators, not just with accelerators, but also with accelerators. Therefore, we will have to think about what we can do with the next accelerator. And as you know, the European community of particle physicists have identified as the most promising project from the scientific standpoint what is called a future circular collider, which is a loop that's 90 kilometers long. It's bigger than a HLC. And this will allow us to do what we have been doing with the current 27-kilometer loop in CNR, electron-positron collider, and then a hadron machine. Whether this kind of machine is necessary, well, this is also proven by a fact. Higgs boson can be produced only by accelerators. There are no other approaches that can allow us to study Higgs boson. Higgs boson is a fundamental element in order to understand these open questions. First of all, because this particle is in itself, well, still quite mysterious. And this gives rise to many important questions, but also because of its special role. The Higgs boson has very different features from all other elementary particles, quantum numbers, for example. It is a bearer of a different power, not a gauge force. It's a Yukawa force. It's such a special particle that we think it might be key in solving some of the open issues that we're faced with. And this can be done only with accelerators. So a larger accelerator, but also more powerful from the technology standpoint. Once again, on paper, in the beginning, it seems like it's a mission impossible, and then slowly but surely, with the perseverance, ideas, and technology, we can get there. And I would like to underline something that I did not mention earlier. HLC experiments and also experiments for gravitational waves, despite their complexity and their difficulty. It's very difficult to build these experiments, and I'm talking about accelerators themselves. At the end of the day, their performance has exceeded in a remarkable way the most optimistic expectations we had. This means that our field and our community is able to deliver the goods, basically. It is able to then implement very complex projects, also sticking to our initial budget without, at least in Europe, without really spending more than was expected, without really increasing our budget. But we can implement these complex projects, which then are able to achieve the targets we had and also even exceed our expectations, as I mentioned earlier. And so I think that this is a milestone for future projects that are even more ambitious than this. At this point, I would like to thank Fabiola Gianotti and Fernando Ferroni in particular. I would like to ask Antonio Zoccoli to stay here with me on stage, where I will listen to one last performance by Umberto Petrin, but let's leave him alone with his art. Let's move away. Umberto, are you here?
Allora, grazie Umberto Petrin.
We thank Umberto Petrin for accompanying us in this event, and this is the last part of the event. We will be talking about the future of the INFN. We have 5 young researchers of the 5 scientific committees, the 5 research lines of the INFN. I'll call them on stage. Leonardo Di Venere, Valentina Mariani, Eugenia Naselli, Gaia Pupillo, Andrea Tesi. You will be you represent the next 70 years of the INFN. Valentina Mariani. Fabiola has told us about what the LHC has done. You can tell us about the future of experiments or your future. I work on a short-term future of the LHC, high brightness of the LHC. This phase will begin in 2027, during which LHC will provide us with a whole lot more data compared to what we have collected so far. If we mention a few numbers, we have about 35 proton collisions. Now we'll have 200 collisions, so a huge leap. And if the LHC will be updated, so will the experiment it conducts have to be updated. And we are strongly committed in this upgrade. And in Perugia, with my group, we are working on the tracker, which is the very heart of the experiment, the core of the experiment. And what we're doing will replace the detector that is currently collecting data, because it would not be able to support the quantity of radiation that we expect for this high brightness process. So the new detector will be more performing and will employ the technologies that is a lot more modern, and it will allow us to collect more and more data in a better way. And this will further drive and shift the boundary of our knowledge. So what can you tell us? I'll tell you more in a few years' time. Possibly something that will help us answer today's questions. Andrea Tesi, INFN department in Florence, the role of theory in inspiring new experiments, and astroparticle physics and space, outer space, accelerators. Where is research heading? Well, theory works a lot better when it is driven, supported by experiments. The best example is the Standard Model, which was suggested at the end of the 1960s based on the data they had, experiment data they had at the time, and that allowed them to look forward, allowed them to form a structure that based on symmetry and principles of simplicity, and trying to blend, unify everything. Obviously, the Standard Model, the way, as we have said several times, explains very well everything we see, explains the whole universe. As the president said, at first we know how the universe works, but we do not know what it contains. One of the open issues, very interesting points for theory as well, is the properties of dark matter. In this context, theory can take cue from the success of the Standard Model, taking cue from the few things we know about dark matter. We know it accounts visible matter is only 4% of the matter that is present in the universe. And starting from this figure, we can try to exploit the principles of symmetry and unification in order to develop theories, further theories. And these experiments allow us to discern and understand what models that have been developed are actually feasible and effective. So theory is absolutely crucial, because it must tell us where we must go. Once we get the theory right, sure, but if we don't have the proper theory, we have to rely on experiments. So what is your dream? What would you like to teach? One of the most interesting aspects of today's cutting-edge research is the use of gravitational waves to better understand the evolution of the universe in its early stages, because gravitational waves can give us information not only on how black holes are formed and what they contain, but they also provide information on the properties of transitions of electron-weak phases. So gravitational waves can tell us more about this. It's still up to you to ask questions. From the body department, Di Venere, literally from Venus, and he deals with astroparticles. He is working on the Fermi experiment on satellites. Tell us more about what we can expect from the deep outer space. One of the aspects of astroparticle physics is that we can observe the universe with different eyes, as we have already heard today. And one of these eyes is provided by the Fermi satellite, which focuses on the energy part of the electromagnetic sphere, the spectrum, the gamma rays. I was lucky enough to work on this experiment from the very beginning of my brief career as a researcher, and I took part in the discoveries we mentioned today, the very beginning of multi-messenger astronomy. So the discovery of the first events, gravitational waves, concurrently with gamma rays and neutrinos with gamma rays. So putting all this together, being part of this community, makes you realize we all study the same thing. We study the same event from a different standpoint, from the standpoints of different experiments. So this multi-messenger astronomy has opened up, is paving the way for future challenges. But dark matter too, which we have mentioned, is one of the major topics we study together with gamma rays through the Fermi satellite, which constantly observes some areas of the universe, such as the center of our galaxy, where we expect to find a large quantity of this dark matter. So we keep on looking for signals of this dark matter, and these signals could be gamma rays. So what is your dream? My dream is to be part of this large community, and I'm already making this dream come true in a way. And clearly, before we can study all this, we have to actually build the satellite. So my dream is to take part in the construction process of a new satellite that can be sent into the orbit and make new discoveries. So I'd like to be part of the operational phase, so tangibly building the tool that is required. The question concerning the dream, we weren't expecting it and we're running late. Eugenia Noselli from the University of Catania, she is graduating and she studies nuclear astrophysics. One of the goals is to reproduce stars in a laboratory. Actually, we are trying to reproduce the nuclear conditions that are very similar to those of the stars. The major aspect is to focus on the main mechanisms that are to be seen in the element that form the universe. We study interdisciplinary subject, astrophysics, plasma physics, and more. And we have recently focused on an innovative experiment which allows us to study radioactivity in these very environments, emulating the conditions of the stars. And again, this is the main goal of the Pandora project, which encompasses the research activities of the university. So what is a stellar environment that gathers ordinary matter, heating it to the point that, and bringing it to a temperature of millions of degrees Celsius, and we must contain this huge amount of energy of heat. We must, and again, technology is crucial in this regard too. We need superconductor magnets that must operate at very low temperature, close to absolute zero. This, again, is not enough because however, is not enough. We also want to study this environment, and to do it, we resort to intense radiation. So we have different eyes, different diagnosis methods that allow us to detect radiations, different energy radiations, ranging from visible X-rays and radio waves to gather overall knowledge. Why should we study radiation? Radioactivity. Radioactivity defines how an atomic nucleus changes into another, how it transforms following a fundamental interaction, which is the weak force. And this also regulates the way our sun and other stars work. And this is due to the fact that these very processes, these transformations, the transformation of the elements of the universe. So we want to study them in this environment because apparently the environment can greatly affect how quickly these transformations can occur. And we'd like to get to know more about that. And when we try to gather more knowledge, we have repercussions on technology as well. For example, nuclear fusion. So hopefully we can help increase knowledge in this very fascinating sphere, which is the knowledge of the universe. Last but not least, Gaia Pupillo. Now that we've heard all her colleagues who are basic researchers, she uses technologies and puts them to good use for society. In Lignano, we have a cyclotron, which is rather special. There are no many accelerators of this kind. There are only 2 in Europe. So in Lignano, we conduct research on astroparticle physics and nuclear physics. I particularly study new methods through the beam of protons produced by the cyclotron to produce radionuclides, which are very useful in medicine. Radionuclides that I have studied over the past years are defined theranostic because their feature is that during their decay they emit radiation that can be used for to diagnose and for therapies as well. So these radionuclides can help us identify radio drugs to better select the patient, understand which patient might be more suitable, and therefore achieve a targeted therapy. This field of research is truly very fascinating for me. It is multidisciplinary. It starts from nuclear physics. It involves radiochemistry, biology, and nuclear medicine. So if we want to, answering the question, we would like to discover new radio drugs. Starting from nuclear physics, because that is, for me, a great opportunity. So I'm very happy to be working on this. Thank you very much. So, young researchers, we were already born when Galileo was conducting his experiments. So they are true, very young to me. So best of luck, and thank you for telling us about the work you're doing. It really can really tell you are enthusiastic about it. So this is it. And closing remarks. So we've gone through the history of the INFN. We have seen where we stand. We have seen where we are heading for. It's a great thing to have dreams and to constantly shift the boundaries of knowledge. That's part of our DNA. I think there's something else we must consider. We've experienced a very complicated moment in time. We must learn from this period. Must learn something from this period. Now that several areas of research, we've seen that areas of research should communicate more. There should be more synergy. They should communicate more and cooperate. We have always tried to give our contribution on specific issues, on very specific targeted issues. But now I think it is high time to pool all the expertise, all the knowledge we have, put it together. We've done this for the pandemic, and we must try to take a step in this direction. So we must focus on better synergy, better cooperation. I think that this historical moment has taught us that, has shown that research is paramount and that cooperation is paramount too. We are already cooperating on an international level, for example. But if we want to further drive scientific research, science must be more interdisciplinary. There must be more cooperation. So hopefully, at our next anniversary, where I'll be sitting in the audience, perhaps in 10 years' time, hopefully we will have experienced an increase in this cooperation. So, unfortunately, we are running late like an old train, and therefore I'd like to thank everyone in attendance. Just 2 more minutes, I'll show you a brief footage of all the INFN presidents in its 70 years of history. Thank you. We must not think that the human mind, when studying the processes of nature, should encounter difficulties and inconsistencies. Now, at the end of the century, we have 2 new forms of astronomy, gravitational waves and neutrinos. These new fields will add further knowledge of the universe. This, together with the 2 other electrosynchrons existing in the world, is the most powerful tool we have for research. It's about that curiosity, scientific curiosity, which leads to better well-being. Great
del pensiero scientifico sono tutte, ripeto, tutte venute totalmente inaspettate. Non se l'aspettava nessuno che dovessero esistere i raggi cosmici.
Visto nello specchio è ancora un evento possibile, quindi classe perfettamente simmetriche rispetto a questa riflessione speculare, e invece è venuto fuori che la particelle è totalmente asimmetrica.
Quindi era una situazione di confusione che si sarebbe chiarita solo dopo il 74 con la scoperta della particella
only after 1974 by discovering the shape-side particle. The closest thing to the Anglo-Saxon vision is the ideal concept.
Il dare quel significato alla parola visione.
Si tratta semplicemente del fatto che esiste grossa materia nell'universo che non emette luce, che quindi ne capiamo l'esistenza solo attraverso l'influenza che ha sugli altri corpi celesti, cioè attraverso le forze gravitazionali. Pesa moltissimo, pesare molto vuol dire necessita una grande energia per essere prodotta, quella che l'universo aveva a disposizione quando probabilmente l'ha messa in giro ai tempi iniziali.
Il Large Hadron Collider del CERN è la manifestazione più alta della nostra capacità di coniugare le nostre
ability to blend our technological skills with the attempt of giving an answer to the final question. Why did the universe
Fino del 1800 siamo in un momento in cui alcuni scienziati dicono addirittura non c'è più niente da scoprire, oramai sono tutti dettagli. E come sempre succede quando si arriva a questo punto e si mette in dubbio il procedere, il processo di avanzamento della conoscenza, avvengono dei fatti speciali, spettacolari che aprono nuove frontiere. Bene, grazie a tutti.
Very well, thank you all for having been with us till the very end. It was a pleasure to be here with you at long last in person. Please let me thank Marco Cattaneo and all our guests who were on stage here with us and who took part in this event. All those who have contributed to organizing this event, the Communications Department, the Office of the President. And please allow me to thank all the researchers, all the technologists, all the technicians, and all the administrative staff who, throughout all these years, have helped us in our research. Thank you.